Welcome back, everyone. We're starting a new chapter today. This is chapter 5 about multiple random variables, and this is lecture 16. In general, this chapter is about experiments that produce lots of random variables. Typically, we'll call these random variables x1, x2, up to xn, where n can be any integer, as large as we like. However, the most common thing we'll study is n equals 2 random variables, and typically with these two random variables, we'll call them x and y. Just a pair of random variables is enough to demonstrate the important concepts of how they are dependent. We also want to know that when we think of this pair of random variables, we can write x and y as a two-dimensional vector. First component is x, second component is y. And more generally, the collection of random variables x1 through xn can be written as an n-element vector. Since the components of this random vector are random variables, we call x a random vector. So this chapter is really the study of random vectors. However, before we get started, our study of how to describe these random vectors, we ought to just reiterate some fundamental first principles. We, uh, we still have an experiment, right? And we still have a sample space for the experiment. And if we perform the experiment, we observe an outcome in the sample space. And then this outcome in the sample space is mapped to maybe a pair of random variables x and y. Or maybe it's mapped to a random vector x1 to xn. This random vector, or in the case of x and y, the pair, is a function of the outcome of the experiment, just as it was for an individual random variable in the previous chapter. Our starting point for the study of two random variables is the joint CDF of x and y. As usual, we denote this with a capital letter F, and now the subscript is the pair of random variables x and y, and similarly we have dummy variables little x and little y. And this joint CDF is defined exactly the way you think it would be, the CDF of x and y at little x and y. It tells you the probability of the joint event that random variable x is less than or equal to little x, and random variable y is less than or equal to little y. The thing is that this joint CDF is a complete probability model for a pair of random variables, but like the CDF for one random variable, it's not so useful and kind of a pain in the butt for analyzing practical experiments. More useful models are, are the joint PMF for two discrete random variables and the joint PDF for two continuous random variables. The joint PDF in particular is useful and convenient because we get to use calculus of two random variables to analyze probabilities in a convenient way. So this chapter has many extensions of things we partly understand already. For instance, we'll consider functions of two random variables and expected values of functions of two random variables. We'll also have extend the idea of independent events to define independent random variables. And finally, at the end of the chapter, we'll consider especially the case where x and y are each Gaussian, and together there'll be something called jointly Gaussian. That will be section 5.9. One of the fundamental models that generates two random variables is the noisy experiment. In this case, we have a random variable x that we want to measure, but instead we make the noisy measurement called y. And so y is equal to x plus z, and z is some kind of a noise random variable. In some cases, z might be an interfering signal. Sometimes it's just noise inside of your detection or your measurement circuitry. Often in these problems, we call x the signal and z the noise. And in many situations, the noise and the signal are independent. We'll be more precise about the notion of independence later, but roughly it's what you would think. It's that the event that x takes on a particular value and the event that z takes on a particular value are independent random variables. So in fact, the way this experiment works is that we have three random variables, x, y, and z, but two of them always specify the third one. And in particular, the noisy measurement y is the sum of the signal x and the noise z. One way to think about the pair of random variables x and y is to think about a plane, an xy plane, of course, axis x, axis y. And what you're going to see is that each outcome of the experiment is a dot on the plane, which specifies an x and a y. For instance, this pair might be the first sample, x1, y1. But you do another example, here is another pair, and another, and another. And somehow what the joint CDF is going to describe is where these dots are likely to appear on the plane when you do the experiment. In the case of the noisy measurements, you have y is equal to x plus z. And if the noise z is small, then what you have is that y is approximately equal to x. And so we know that the line y equals x is just the 45-degree line. And if y is approximately equal to x, then you should see samples of x and y that are close to each other, like along the line x equals y. On the other hand, maybe you're an archer and you're in a competitive archery contest and you're aiming for the bullseye at the origin. And in that case, your samples X and Y might measure your position on the XY plane where your arrow lands. And you would expect that somehow your XY pairs will be random but close to the origin, and that maybe far away points like this one will be hopefully infrequent. Okay, so let's jump to section 5.1 where we introduce and analyze the joint cumulative distribution function. Given random variables x and y, we know that x is described by the CDF fx of x, and y is described by the CDF fy of y. However, when we do an experiment that generates both an x and a y, and they may be related in some way, the individual CDFs of x and y are not enough. Instead, what we need is the joint CDF of x and y that tells us not just the probability of the individual events, x less than or equal to x and y less than or equal to y, but it tells us the probability of the joint event. Going back to thinking of x and y as a point on the xy plane, a randomly chosen point, what the joint CDF is telling us is it's if we have a point xy here, then the joint CDF is telling us it's the probability that the pair we observe lands in this box where to the left of this line, x is less than or equal to x, and below this line, y is less than or equal to y. Keep in mind that this looks like a box, but actually it goes off both for x's to the left all the way back to minus infinity, and for y's below little y all the way down to minus infinity. Because the CDF is a probability, it inherits many of the properties of probabilities. For example, we see that the joint CDF of X and Y is always greater than or equal to 0 or less than or equal to 1 because probabilities are between 0 and 1. For property B, we observe that the joint CDF of X and Y at infinity and infinity, well, that's the probability x is less than or equal to infinity, and y is less than or equal to infinity. And because x and y are properly defined random variables, they're always less than or equal to infinity, so this has to equal 1. You can also use the joint CDF to find the individual CDFs of x and y. So looking at property C, we have that if we take the joint CDF of x and y and evaluate at little x, but let little y go to infinity, this is the probability that x is less than or equal to little x and y is less than or equal to infinity, but y is always less than or equal to infinity. So this is just the probability x is less than or equal to little x, but that's just simply the CDF of x. So from the joint CDF, you can recover the CDF of x. And similarly, if we reverse the roles of x and y, and we let little x go to infinity, and we fix little y, this is the probability x is less than or equal to infinity, which always occurs, and y is less than or equal to little y. And this is simply the probability y is less than or equal to little y, and that's the CDF of y. Properties E and F tell you what happens to the joint CDF when either little x or little y goes to minus infinity. So for instance, looking at property E, this is the probability x is less than or equal to little x, and y is less than or equal to minus infinity. But this is contained in the event that the probability y is less than or equal to minus infinity, and that's equal to the CDF of y at minus infinity, and that's equal to 0. So in fact, that if either little x or little y is minus infinity, then the joint CDF is 0. So we handled the little y case in property E, and we see the exact same thing with the role reversal of x and y in property F. And then finally, in property G, we have our last property, and it's that the idea that the CDF is an increasing function is now generalized to two variables. So if x is less than or equal to x1 and y is less than or equal to y1, then the CDF at x and y is less than the CDF at x1 and y1. The idea here is kind of simple. It's that imagine we have a pair x and y, and now we choose another pair, x1 and y1, and x is less than x1 and y is less than y1. And what this property is saying is that the probability you're in this box with upper right corner x and y is less than or equal to the probability you're in the bigger box with upper left corner x1 and y1. So here's an example of an experiment where we use the joint CDF to model a pair of random variables x and y. In particular, x is the age of a child entering first grade, and y is the age of a child entering second grade. And the joint CDF of x and y is given by this kind of complicated expression on the right side here, which has 6 different cases. Some of these cases are kind of obvious. For instance, if x is less than 5, right, then the joint CDF is 0. In fact, what that first case is the probability x is less than 5 is 0. And the second case says that the probability that a child entering second grade is less than 6 is also equal to 0. But frankly, this is a really simple model of an experiment. In fact, what the CDF is saying is that children entering first grade are between 5 and 6, and children entering second grade are between 6 and 7. But here we have 6 cases, and the way the CDF presents the information is kind of written in a super confusing way. This example asks you to find the individual CDFs of X and Y just to make this fact that it's confusing a little bit more clear. So for example, if I think about the CDF of X, to solve this problem, we use the property from our earlier theorem that the CDF of X is equal to the joint CDF of X and Y at X and infinity. The next step is to see at little y equals infinity, which of the above rules for the joint CDF still apply. So for example, the first rule holds at y equals infinity. And so what we get is that the CDF of x is equal to 0 for x less than 5. The next rule doesn't hold for y equals infinity. Neither does the third rule, neither does the fourth rule. But when we look at the fifth rule, we have y greater than or equal to 7. That includes y, little y equals infinity, right? And so we have another rule that applies. We have x minus 5 for 5 less than or equal to x less than 6. And then finally, we have the one otherwise rule, and that rule also applies. And now we have a CDF for x, and the CDF for x starts at 5, goes to 6, and it's 0 for x less than 5. And then it jumps as a ramp up to 1 at x equals 6. And then it continues and it's flat. So what we see from this example is this is our familiar ramp, the CDF of a continuous uniform random variable. So we can conclude that x is a continuous uniform 5, 6 random variable. If you do the same thing for y, you would find out that y is continuous uniform 6, 7, because second graders are 1 year older than first graders. So in fact, x and y are something really simple, but this is kind of hidden by this joint CDF. So this slide summarizes what we just found, that x has a CDF that's a ramp function between 5 and 6, showing that x is continuous uniform from 5 to 6, and y is a ramp function from 6 to 7, showing y is continuous uniform between 6 and 7. In a lot of probability calculations, you're interested in calculating what is the probability x is in some interval between x1 and x2, and y is also in some interval between y1 and y2. Conceptually, if we go back to thinking about our xy plane, we have x1 to x2, y1 to y2. We have x and y, and what we're calculating is the probability that the xy pair is in this box. You can do this calculation using the joint CDF, but it's going to be complicated. The first step is to say, well, it's the probability x and y, x is less than equal to x2, and y is less than equal to y2. So we're calculating the probability we're in this box. So this is counting uh, the probability we're in anywhere in this pink shaded box. So this is clearly overcounting the probability of being in the box we're actually interested in. So the next step is to try to subtract away the probabilities of areas that we're not actually interested in. The first area we'll subtract is the probability x is less than x2 and y is less than y1. That corresponds to subtracting away probabilities of x's and y's in this box. And then from there, we'll also subtract away the probability of x is less than x1 and y is less than y2. That corresponds to subtracting away probabilities of x's and y's in this green box. Now we're pretty close, but in fact, what we did is we double counted, or I should say double subtracted x's and y's here in this lower left corner box. And those we have to add back in. And so now we have, using the joint CDF, 4 different ways. We have a way of calculating the probability that the XY pair is in a particular box. I think it's fair to say that this procedure is doable, but at best messy and complicated. Things should be simpler than this. So here we are at quiz 5.1. It means we've arrived at the end of section 5.1, and you should be able to take the quiz and make sure you understand what's going on. And if you took the quiz and finished it and it went okay, then my next suggestion is to do problem 511. It's almost as simple as the quiz, but a little bit different. And so let's end this part 1 of this lecture here, and we'll start part 2 by doing the quiz and solving this problem and moving on to things that are less complicated and more useful than the joint CDF.